People love to say light is both a wave and a particle. It sounds clever. It sounds deep. It sounds like physics doing something mystical. But if you stop and think about it for more than 10 seconds, it doesn't really explain anything. It's just two words taped together. What does it mean to be both? When I throw a ball, it's not also a ripple in the air. When I make a ripple in water, it's not secretly a pebble. So when someone says light is both a wave and a particle, I want to ask a very annoying question. In what sense exactly? At the same time, or just sometimes? And how do you decide? Usually the explanation goes like this. When light spreads out and interferes, we call it a wave. When it hits a detector in little clicks, we call it a particle. That's not an explanation. That's a filing system. You're just saying, when it behaves like this, I use this word. That doesn't tell me what's actually going on. Take a very ordinary example. You turn on a dim light and let it shine on a screen. If you turn it down far enough, the screen doesn't glow smoothly. You get tiny flashes, little dots. One here, one there. That sure looks like particles. But if you leave it on long enough, those dots pile up into a pattern. And the pattern has stripes, just like waves interfering in water. Now, what are you supposed to say? That each particle somehow knew about the wave pattern ahead of time, or that the wave secretly breaks into particles when you're not looking? People used to argue about this. Isaac Newton thought light was made of little bullets. Albert Einstein later showed that light sometimes behaves as if it comes in chunks of energy. On the other hand, experiments with slits and screens scream wave behavior. So we're tempted to shrug and say, well, it's both. But that's giving up too early. Here's the problem. Wave and particle are ideas we invented to describe familiar things. Water waves, dust particles. They come from our everyday experience of pushing stuff around. Light doesn't come from that world. It's not a tiny marble flying through space, and it's not water sloshing up and down. Those are pictures we borrow because we don't have better ones. Imagine a machine that fires paintballs, but the paintballs don't fly straight. Instead, each one spreads out, explores many paths, and then suddenly leaves a single splat on the wall. If you saw that, you wouldn't say, it's both a paint splash and a bullet. You'd say your idea of paintballs is wrong. That's where we are with light. The real question isn't whether light is a wave or a particle. The real question is why we keep needing those words at all, and what replaces them when they stop working. And to get there, we have to look very carefully at what we actually observe, not what we wish were happening. Because once you do that, the whole wave-particle business starts to look like a distraction from something much stranger. All right, let's slow down and be stubborn about facts. Not philosophy, not words, just what actually happens when you do experiments. You set up a light source, a couple of narrow slits, and a screen. This is a real piece of metal with holes in it, a real lamp and a real screen you can walk over and touch. No metaphors yet. When the light is bright, you get stripes. Bright, dark, bright, dark. If you've ever played with water waves in a bathtub, you recognize the pattern immediately. So you say, fine, it's a wave. Now you do something cruel to the experiment. You turn the light way down, so low that the detector only clicks once in a while, one little dot at a time. There's no half dot. There's no smeared dot. Each hit is localized, one place, one event that smells like a particle. But here's the uncomfortable part. You don't get to choose one description and throw away the other, because even when the dots come one at a time, the final pattern is still stripes. Each individual hit is unpredictable, but the statistics are not. After 1,000 hits, the pattern emerges. After 1,000,000, it's unmistakable. So what traveled from the source to the screen? If it was a particle, it somehow knew about both slits, even though it only hit the screen once. If it was a wave, why did it arrive in a single dot instead of a little ripple everywhere? People often say, well, before measurement it's a wave, and after measurement it's a particle. That sounds nice, but it's dangerous. Measurement of what exactly? The screen isn't a mystical device. It's atoms, electrons, electric forces. If light suddenly changes its nature just because it touches something, then we'd better explain what makes that touch so special. Usually that explanation never comes. Let me give you another concrete situation. You have a Geiger counter clicking when radiation hits it. Each click is sharp and discrete. You never hear half a click, but the rate of clicking follows smooth mathematical laws. The same story again. Discrete events governed by a wave-like rule. So maybe the mistake is assuming that waves must be continuous and particles must be localized. That assumption comes from our experience with water and sand, not from nature's rule book. Here's the key idea, and I want to be very careful with it. The thing that behaves like a wave is not the energy splat on the screen, it's the probability. The rules that tell you where a hit is likely to occur behave like a wave, peaks and valleys, interference, cancellation, reinforcement. But probability is not a physical substance. You can't scoop it up. You can't spill it on the floor. So saying the probability waves is already telling you that you're not talking about a thing moving in space the way a ball does. At the same time, the detection events are real. They happen at a place and a time. You hear the click. You see the dot. So we're stuck with a theory that gives you wavy predictions and point-like outcomes. If you're honest, you'll admit this doesn't fit into either classical box. It's not a wave in space, and it's not a particle following a path. It's something else entirely, and we're forcing it into familiar shapes because we don't like admitting that our intuition has run out. And once you accept that, the next question becomes unavoidable. If light isn't really a wave and isn't really a particle, then what exactly is it that's evolving between the source and the screen? Now, people usually jump in here and say, the wave is just a mathematical thing, and that's closer to the truth. But it still feels slippery. Mathematical thing doing what exactly? Let's talk about equations, but without worshiping them. An equation is not reality. It's a machine for predicting what you'll see next. If the machine works, you keep it. If it doesn't, you throw it away, no matter how beautiful it is. In classical physics, waves were honest. A water wave meant the water was actually going up and down. A sound wave meant air molecules were bumping into each other. When James Clerk Maxwell wrote down equations for light, it looked the same way. Electric and magnetic fields wiggling through space. So naturally everyone thought, okay, light is a wave of something. But then came experiments that refused to cooperate. Light dumps its energy in chunks, always chunks. You can make the chunks smaller by lowering the frequency, but you can't smear one out. That's not how classical waves behave. So what did we do? We kept the wave equations because they predicted interference perfectly. And we added a rule that says energy comes in packets. That hybrid worked numerically, but conceptually it was a mess. Let me give you a mechanical analogy that almost works and then fails, which is usually where learning happens. Imagine a stretched rubber sheet. A vibration spreads out like a wave. Now imagine tiny mouse traps glued to the sheet. Each trap snaps only if the vibration is strong enough at that spot. The wave spreads smoothly, but the clicks are discrete. That's a cute picture, but it cheats. The rubber sheet is real. The vibration is physical. With light, the sheet is not something you can point to. There's no medium sloshing around. And worse, you can send just one photon at a time and still get the same interference pattern. There's no background wave to carry it. So the wave isn't a hidden physical vibration in space. It's something else. It's a rule that tells you how likely different outcomes are. This is where people get nervous and start using mystical language. Don't. There's nothing mystical here. It's just unfamiliar. The object that evolves smoothly is not energy, not matter, not a particle, but a complex valued function that gives probabilities when you square it. That's it. That's the whole trick. You can call it a wave function if you want. The name doesn't matter. What matters is what it does. It spreads. It interferes with itself. It adds and cancels. And then when you interact with something big and noisy like a detector, you don't see the function. You see an event. The mistake is thinking the wave function is a physical wave like water. And the second mistake is thinking the particle is a tiny object flying along a path when nobody's watching. Both pictures sneak in classical assumptions that don't belong. Here's the brutal fact. Between emission and detection, light does not have a definite position, not hidden, not unknown, not secretly waiting. It simply doesn't have one. The theory doesn't assign it one, and experiments punish you if you try. So when someone asks, where was the photon before it hit the screen? The honest answer is, that question doesn't apply. And that's not philosophical evasion. That's respecting what the predictive machine actually says. And now the discomfort deepens. Because if light doesn't travel as a particle along a path, and it doesn't ripple as a physical wave in space, then what does it mean to say it travels at all? People get very upset at this point. They say, come on, something has to be there. And I sympathize. We grew up in a world where things are either here or there, moving along paths, bumping into other things. But nature doesn't promise to fit our childhood categories. Let's poke at the idea of a path. because that's where most of the trouble hides. If I throw a baseball, I can mark its position at every moment. If I use a better camera, I get a smoother path. The idea of a trajectory makes sense because the baseball always has a position whether I look or not. That assumption works beautifully for big things. Now try the same trick with light. Put detectors along the way. Ask, which slit did it go through? The moment you insist on answering that question, the interference disappears, not because the light got shy, but because the conditions of the experiment changed. You didn't just observe, you interfered. This isn't about human consciousness. That's another word people use when they're confused. A rock could do the measuring. Any interaction that records which path information wrecks the interference. So the problem isn't that light hates being watched. The problem is that the idea of a path is incompatible with the interference pattern. You can't have both. If the experiment allows you to say it went through slit A or slit B, then the wave-like prediction vanishes. If the experiment is set up so that those questions are meaningless, the interference comes back. That tells you something very sharp. The notion of a path is not an innocent description. It's an extra assumption. And when you add it, the theory breaks. Here's another example. Suppose you have a mirror system that bounces light around in a complicated way. If light were a little bullet, it would ricochet along one route. But the equations say something else. They say all allowed paths contribute, not one, all of them. Some cancel, some reinforce. The final result depends on the whole pattern. That's not poetry. You can calculate it, and the calculations work frighteningly well. So when you ask, which path did the photon really take? You're asking for information the theory never promised to give you. It's like asking what the color of Tuesday is. The grammar looks fine, the question isn't. Now here's the part that really irritates people. Even if you don't measure which path the light still arrives as a single dot, one place, one time, no half measures. The wave-like thing doesn't smear into reality. It gives probabilities, and reality chooses one outcome. But notice what's missing. There is no little particle traveling along one definite route and then magically consulting a wave at the last moment. That story is something we made up to feel better. Instead, there is a smooth evolution of probabilities and then a discrete event. Both are real. Neither is the other. Calling one a wave and the other a particle is mixing up the map and the territory. The unsettling lesson is that classical questions like, where is it right now, don't always make sense. They work when they work, and they stop working when they don't. Physics isn't obligated to answer questions that come from bad assumptions. So the wave-particle duality isn't a deep truth. It's a warning sign that you're using the wrong mental furniture. And once you see that, another question becomes unavoidable. If light doesn't have a path, and it doesn't have a position until it's detected, then what exactly is conserved, carried, and transmitted from source to detector? At this stage, people usually retreat to something safe. They say, all right, maybe position is fuzzy, but energy is real. The photon carries energy from here to there. That sounds solid. Energy feels dependable. You can burn things with it. But even that idea needs care because energy is not a substance you can point at either. It's a bookkeeping rule, a very good one. It tells you what can happen and what can't. When a photon is absorbed, a definite amount of energy shows up. An electron jumps, an atom vibrates, a detector clicks. That part is sharp. But between emission and absorption, where is that energy? Is it flowing like water through a pipe? If it were, you'd expect it to be distributed along the way. It isn't. Here's a concrete example. You shine light on a metal and electrons pop out. This is the photoelectric effect. Below a certain frequency, nothing happens no matter how bright the light is. Above it, electrons fly out immediately, even if the light is very dim. That tells you energy arrives in whole units tied to frequency, not spread thin like a wave's intensity. So you're tempted to say, aha, the photon carried the energy as a particle. But be careful. The same light, under different conditions, produces interference that depends on paths that energy could not have followed if it were localized the whole time. Another example. Put a detector halfway along the path and make it perfectly absorbing. If it clicks, the energy is deposited there and never reaches the screen. If it doesn't click, the interference pattern on the screen changes as if that detector were never there. There's no evidence of half energy passing by and deciding later what to do. So energy conservation works beautifully at the endpoints, emission and absorption. In between, the theory doesn't describe energy as sitting at a point in space the way a marble does. The conservation laws apply to outcomes, not to imagined trajectories. This is deeply uncomfortable if you're attached to mechanical pictures. We want to imagine something moving continuously, carrying its properties with it. But quantum mechanics doesn't describe that story. It describes correlations between events. What is really transmitted is not a little packet traveling through space. It's a set of possibilities constrained by precise rules. The wave function encodes those constraints. It evolves according to equations that conserve probability in a strict way, even though individual outcomes are unpredictable. Think of it like this. If I give you a fair die and tell you the rules of rolling it, I've transmitted information about probabilities, not a specific outcome. The outcome only appears when you roll. With light, nature does the rolling at detection. But don't push that analogy too far. Unlike dice, the probability structure itself can interfere with itself. That's the new ingredient. Probabilities aren't just numbers. They have phases. They can cancel. That's why the stripes appear. So what arrives at the detector is not a wave and not a particle, but a rule book that suddenly produces an event. If that feels unsatisfying, good. It should. Because we're very close to the real lesson now. The final mistake people make is thinking that the wave and the particle are properties of light itself instead of properties of the questions we ask. And that leads straight into the most important point of all. Here's the turning point. The thing that's been misleading us all along is the belief that words like wave and particle describe what light is. They don't. They describe what we ask it to do. When you build an experiment that asks, how does this spread? You get an answer that follows wave mathematics. When you build an experiment that asks, where did it land? You get a localized event. You don't get both answers at once because the questions are incompatible, not emotionally, physically. This is not a limitation of our instruments. It's a limitation of the questions. You cannot design an experiment that simultaneously demands a precise path and interference because those demands contradict each other. This is where people often invoke something mysterious like complementarity as if naming it solves the problem. It doesn't. It just tells you to stop asking for a single classical picture. The deeper lesson is simpler and more unsettling. Physical theories do not tell you what things are in isolation. They tell you what happens when things interact. Light is not defined by a hidden essence. It is defined by the rules that connect preparation to outcomes. So asking, is light really a wave or a particle, is like asking whether a chess move is really aggressive or defensive. The answer depends on the position. The question assumes a property exists independent of context. It doesn't. Let me ground this with one more concrete example. Suppose you have a setup where light can take two routes to a detector. If the routes are indistinguishable, you get interference. If they're distinguishable, you don't. There is no in-between story where light secretly picks a path but still interferes. The pattern changes discontinuously when distinguishability changes. That's telling you something sharp. The theory is not about hidden behavior behind the scenes, it's about observable distinctions. When distinctions exist, the math changes. When they don't, the math changes back. So wave-particle duality isn't a paradox to be solved. It's a symptom of forcing classical categories onto a theory that never promised to respect them. Light is not switching costumes depending on your mood. It's obeying a single consistent set of rules that look wave-like in their predictions and particle-like in their outcomes. Once you stop demanding a picture of what it really is, the confusion dissolves. You don't need light to be both wave and particle. You need a framework that predicts interference and clicks without contradiction, and we already have one. Now comes the final step, the one that people often resist because it sounds like philosophical retreat, but isn't. If wave and particle are the wrong questions, then what is the right way to talk about light at all? That's where everything finally snaps into focus. So here's the clean ending, with no drama and no mysticism. Light is not both a wave and a particle. That sentence pretends to explain something, but it actually hides the real structure of the theory. Wave and particle are classical ideas. They come from water, sand, bullets, ripples. Light does not belong to that family. What light actually does is this. There is a mathematical object that evolves smoothly and locally according to precise rules. That object lets you calculate probabilities for different outcomes. Those probabilities can interfere, cancel, and reinforce. Then when light interacts with something big enough to register a result, you get a single definite event. That's it. There is no tiny marble flying through space. There is no physical ripple sloshing through an invisible medium. There is no secret switching between personalities. There is just a theory that predicts experiments and experiments that confirm it. When people say light is a wave, they usually mean the predictions obey wave equations. When they say light is a particle, they usually mean the outcomes come in discrete chunks. Both statements are true. Neither one tells you what light is. And that's not a failure of physics. It's a correction of our expectations. We're used to theories that let us visualize everything in terms of little objects moving around. Quantum mechanics doesn't do that, and it doesn't apologize for it. If you insist on a picture, you'll always end up smuggling in contradictions. If you accept that the theory is a rule book connecting what you prepare to what you observe, the contradictions vanish. So the honest thing to say is not that light is both a wave and a particle. The honest thing to say is that light is quantum mechanical. And quantum mechanics does not describe objects the way classical language demands. That answer feels unsatisfying only if you think understanding means being able to draw a picture in your head. But real understanding is knowing what you can predict, what you can test, and where the questions stop making sense. Once you see that, the wave-particle paradox isn't a paradox at all. It's just the moment you realize that nature isn't required to use our favorite metaphors.